Welcome, guys and girls, to another exciting session of chemistry. For those of you who don't know about this channel, I'm going through the new AQA spec for chemistry, and I'm going to go through chemistry, biology and physics. So what we're looking at today is we're going to be looking at the history, if you like, of the periodic, or of the atom rather. Now, so from the last topic, what we saw was that we hold the following model of the atom to be true. So we have our nucleus, which contains both protons and neutrons, and around the nucleus we have electrons. So this is just a completely made up element. It doesn't exist, but it's just to make the point. So this inside bit here, where you've got the blue and the purple, is called the nucleus. Now the nucleus, as we learnt, is made up of protons and neutrons, and on the outside we have the electrons. So here are my electrons. Now the question is, how do we know all of that? And that's what we're going to be looking at today. So we're going to be looking at the idea of the evolution of the atom and how people came to discover it. So the first person we're going to be looking at is John Dalton. So in the early 1800s, this guy, John Dalton, had an idea. He looked and he made observation, and what he saw was that when you react things together, when you react chemicals together, to be more specific, they end up making new products. And so the way he thought about it in his head was that, let's take, for example, I'm going to give you an example just to illustrate this. Let's say you're talking about carbon. So you've got carbon plus oxygen going to make carbon dioxide. So the first thing what you would notice is that carbon is, for example, coal, and you're going to react it with oxygen in the air and it'll make a completely new product, carbon dioxide. So the way he envisaged this, and this is John Dalton's idea, was that each element or each type of thing that you're reacting will have a specific shape, and it will have atoms that are specifically shaped, and when you react them together they are rearranged differently. So this would be the green triangle for the carbon, and then we've got the blue for the oxygen. And so can you see that his idea is that you start off with specific atoms. So here's my carbon atom, there's my oxygen atom, and then they're rearranged to make a brand new compound. And this was his idea, and what he thought at the beginning was that these atoms, so this atom, this atom, this atom, that they are indivisible. These are the smallest parts of anything. So everything are made from atoms, and atoms are indivisible. To put it in an easier way, he believed that atoms are indivisible. Indivisible. So in other words, that you can't get smaller parts than an atom. This, of course, was wrong. And so we're going to look at next what the other models are and how the idea was developed. Because of course we know that an atom is made up of electrons, protons and neutrons, but the only question that remains is, well, how do we prove that? And who proved it, and how did they prove it? So J.J. Thomson is the second guy. J.J. Thomson, with no P. J.J. Thomson was quite a clever guy as well, they all are. And what he did was he used a cathode ray tube. Okay, so here's my cathode ray tube, and at one end there's going to be a tiny slit. So here there's a tiny slit. Can you see that gap there? Brilliant. So what he does is he ends up connecting a power source to it. So here's my symbol for a power source. You learn that in physics. That power source, of course, has a positive and a negative side to it. And so what he did was, as he applied a potential difference or a voltage of about 15,000 volts to it, he noticed that it caused a beam of light to shoot across. Okay, so it shoot across. It went straight into the slit. It went straight through the slit, and on the other end, so it was closed. On the other end, it caused a light to form. So what he did was he was like, okay, let's see how this actually behaves, this light that's being produced, this beam that's being produced. So what he did was he put a positive, let's change the color, put a positively charged and a negatively charged plate across the area where the light was going through. And when he did that, what he began to notice was, instead of following this straight line, the ray actually started to bend in the direction of the positively charged plate. So what does that prove? Well, this proves that this ray, whatever it is, negatively charged. And why does that prove that? It's because it's moving towards the positive, and as we know, opposite charges attract. So he concluded two things really. Conclusion number one is that the beam is negatively charged, and number two is this negative charge must be cancelled out, particle rather, not ion. Particle. Right, so that's what he did, and so he proposed a specific model. What he said was that an atom, number one, why was this a big deal? Because number one, it disagreed with John Dalton. If you remember, John Dalton said that the particles are indivisible, right? That the smallest part of a particle is the atom. There's nothing else smaller than an atom. Well, what he proved is that there is something smaller than the atom. It's the electron, right? So he discovered the electron, and he hypothesized that there'd be a positive proton. And so what he said is that the best way to explain this is the plum pudding model. In today's dessert way, we'd say it's the a cookie, a chocolate cookie, right? So the idea is the same. So what he said, if I draw my key here, what he said is that surrounding, like the chocolate cookie bit, would be the electrons. So that's my electrons, and here surrounding the electron, all around, right, all around, every single place, is going to be the positive area. So these are the protons. So what he thought is that the positive is shared all around the area of the atom, so that it cancels out the negative charge. So he said that this has a negative charge, and that the protons are positive charge, and so that overall they cancel out. Now it turns out that this was a good model, however it also turns out to be wrong, and so we're going further into the evolution of the understanding of the structure of the atom. So let's see who's next.